Hello, my name is Mary Olson. I'm the founder of Gender and Radiation Impact Project. And I have a recording with some slides called a short shot. And these are part of our series on radiation information for everyone. We're doing online courses on radiation, biology, and society. And this is a collaborative process between Gender and Radiation Impact Project and Beyond Nuclear. This short shot is on radiation terms. It's really a 101. It's a walkthrough of the language of radiation and has to be qualified, since this science, more than most, is riddled with disinformation, intentional or not. Here from the US Congressional Record is a quote: "Keep them confused." President Eisenhower told the Atomic Energy Commission in about 1953. Leave thermonuclear out of press releases and speeches. Also, fusion and hydrogen. The agency complied. Only decades later, in 1979, did the public learn of this obfuscation. Those words are from the testimony of Honorable Ed Case of Hawaii on the event of the 51st anniversary of the detonation of the world's first thermonuclear device at Enewetak Atoll in the Marshall Islands. That was October 29th, 2003. Keep them confused. A little humor here, but confusion is the point. So we're going to walk through these terms, and I'm going to use them repeatedly in hopes that you can begin to hear them. An radioactive or unstable atomic nucleus is the topic of this slide. An atom has a nucleus, and one or more electrons orbit around it. I put quotes on orbit because that's kind of an old idea. But if the atom's nucleus is stable, it is made of an equal number of subatomic protons and neutrons. If it is stable, it is not radioactive. If an atom is unstable, it is radioactive, and its nucleus contains an unequal number of protons and neutrons. This mismatch may be an excess of either protons or neutrons. Having an unequal number of protons and neutrons results in an excess of energy in the atomic nucleus, which must be discharged, which will then make it stable. When particles and waves, radioactivity, are discharged, they carry much of that excess energy with them. All radioactive elements are headed towards a stable nucleus sooner or later. You know, my mom always used to say, everything's heading towards healing. I wonder if that's sort of the same idea. Okay, stable and unstable isotopes. In general, an element is called radioactive if the nucleus is unstable. The same chemical element can come in different forms, or isotopes. The different forms are called isotopes, and some are stable and some are unstable. For example, hydrogen, or H1, the kind we're used to that'll explode in a pure situation with a spark or make up part of a water molecule, is stable. I should say a normal water molecule, because all three of these will actually bind into a water molecule given an open oxygen. So hydrogen 1 is the one that's stable. Hydrogen 2, or deuterium, or heavy water, is also stable. It's not radioactive. But hydrogen 3 which has 3 protons, is unstable and radioactive. And we have a whole separate recording on tritium. The decay process may happen with 1 or more decay events or steps before the atomic nucleus is stable. There are many steps in the decay chain of uranium, for example. Typically, a new element has formed when stability is achieved with a new name. The end of the decay chain for uranium is lead. Here's another example. Phosphorus 32 decays to sulfur 32 in 1 step with the emission of a beta particle. This picture in the public realm shows the 3 isotopes of hydrogen: protium, deuterium, and tritium, or P1. Excuse me, misspoke. 1 proton is H1. Deuterium has a proton and a neutron, and tritium has a proton and 2 neutrons. Radioactive decay, radioactivity. Again, a decay event is the emission of a particle or wave from the unstable nucleus of a radioactive atom, also called a radionuclide. Conversely, decay is also called radioactive emission and results in some or all of the excess energy in the unstable nucleus being emitted. If that emission only reduced part of the excess energy in the nucleus, there will be another emission or decay event at some point. Radioactive emissions can be counted with a radiation detector. The unit for radioactive emissions is the becquerel or the Curie. BQ for becquerel, CI for Curie. Here's the picture of an alpha particle being emitted from an atom. The alpha particle looks like a helium atom, by the way, 2 protons and 2 neutrons, but it is energetic, it is moving, and any impact it makes on a surface or on a cell will transfer that energy. So here we come to radioactivity, waves, and particles. Radioactivity is part of the electromagnetic spectrum. Radioactivity is a class of events, these emissions, these bursting forward of particles and waves, those are events, and these include X-rays, gamma rays, neutrons, both fast and slow, beta particles, alpha particles, and excited photons. The particles are primarily a hazard when emitted inside the body, when the radioactive elements have been inhaled or ingested before the decay event. So the particle or wave comes out of the element while it is inside a body. That is where the particles have the most hazard. So this picture shows the penetrating ability of the various types of particles and rays. And I have a phrase here: watch out, particle size prevents penetration of skin. However, particle size makes beta and alpha more destructive if emitted inside the body. They are basically the alpha particles like a cannonball because it's so big. Radioactivity, radiation. How many times can we go through this? Well, it's a little bit of detail here. Radioactivity is an emission of a particle or wave that reduces the excess energy in an unstable nucleus. An element is highly radioactive if it emits particles and waves rapidly and will have a short half-life. Some radioactive elements rarely emit radioactivity. These have a long half-life. Radioactivity creates a field of ionizing energy or radiation that can be measured directly with an appropriate detector. When radiation comes in contact with a living cell, then the cell receives an exposure to radiation. Radiation impacts non-living matter causing accelerated material aging. Think about atomic reactors constantly being exposed to radiation. Components are accelerated in the aging of the metal or plastic or whatever the material is. How to limit external exposure from gamma, X-ray, or strong neutron emitter. This is from the Nuclear Regulatory Commission's website. It says less time spent near the source, less radiation received. Greater distance from the source, less radiation received. Behind shielding from source, less radiation received. So sometimes these sources are near our home and for reasons beyond our own control. This image from the US Nuclear Regulatory Commission website suggests that running away is our best option. What right does anyone have to do this to a local community? Why avoid the term dose? Radioactivity radiation can be measured with the proper tool to some level of certainty. See your user guide. Some detectors measure energy directly, and this is expressed in units like electron volts or EV, joules, gray, and rad. Other devices register counts, which report radioactive emissions. The unit for the counts is becquerel or curie. The device may offer a conversion to dose, which includes an algorithm based on hidden mathematical models. Dose is a statement of both exposure and radiation harm to living cells, expressed in units of sieverts or rems, also can be therefore millisieverts and millirems, which are smaller units. These units express a factor for relative biological effectiveness, which is harm. Effectiveness means causing damage. If the exposure is from anything other than an external source of X-rays or gamma rays. In other words, there's a relative biological effectiveness value for betas and alphas and neutrons. Dose is always derived from a model, and there are assumptions in that model that include the size, shape, sex, and age of the body who is getting the dose. I put my friends from International Medcom's detector on the left. The one on the right is a more typical unit that you would see in movies, etc. Nuke speak. Nuke speak is the use of metaphor, euphemism, technical jargon, acronyms to portray nuclear concepts in a neutral or positive way. Most succinctly put, quote, keep them bored or ashamed of not understanding. At Radiation Information for Everyone, we want your questions, comments, and to help reduce confusion. Please tune into the short shot on fission for help with the term half-life and other matters. Here is a list of citations. We will also post these slides so you can more easily access these links. Thank you so much and stay safe.